Hello and welcome to Eaton's Technology Summit for Data Centers and Energy, coming to you from Madrid. I'm Emma Stratton, I'm Head of Channels at DCD, and I'm joined by Peter de Bock, who is the Vice President for Data Center Energy and Cooling at Eaton. So thanks for joining me, Peter. How are you?
Nice to be here. Thank you.
Oh, fantastic. Thanks for joining me. So to start us off, are you able to tell me a little bit more about you, your career journey, and your role at Eaton?
Sure, be glad to do so. Um, I've been at Eaton now for almost 1 year, and at Eaton as a VP in data center energy and cooling, I work at the CTO office and I explore what the technologies are that are coming next that we should work on as a team to make sure that we're competitive in the future. Prior to Eaton, I was a program director at ARPA-E for the US Department of Energy, funding research in data center cooling throughout the entire United States. And before that, I had a career at General Electric as a principal engineer in thermal sciences.
Okay, fantastic. So, um, this conversation is all around designing AI infrastructure as a complete system. So, to start us off, you able to talk a little bit around how high density workloads have led to a shift in a more system level design?
Yeah, one thing you have to think about when you talk about AI loads, that in AI, training or inferencing workload is much larger and it spans multiple processors, multiple servers, and perhaps multiple racks. That means that a lot of these systems have to work in concert together, in tandem. They all have to operate in the same computational problem. Where you're looking at smaller workloads, they can really be shifted from one server to another quite easily. When all the servers have to work together, they all have to have the same, they all have to work. If one of them slows down, the entire system slows down. And that means that we need to work to a higher level of reliability, both on the power side and the cooling side. All these servers have to operate, uh, I think, in the future with even higher levels than tier 3 or tier 4 reliability. In my background, where I also worked on aerospace systems, I worked on systems that can operate to 9 nines of reliability, which is the FAA standard for certifying equipment for human flight.
Yeah.
We might not have to go that far, but maybe more than tier 3, which is 99.982%. I see as a, maybe shifting that to 4 or 5 or 6 nines, very feasible, because you're looking at enormous energy workloads, enormous cooling workloads, and enormous computational workloads that have to work as a much more powerful system than an low energy enterprise workload.
Yeah. Yeah, absolutely. Kind of what are the other main consideration factors when power, cooling, and rack controls are sort of one complete system?
Yes, currently you see that a lot of the systems we have built over the years have come together from experience within our own expertise areas. So we have people that are very experts in CDUs, like our friends at Boyd Thermal, which is now part of Eaton. Or our friends at Eaton that make the UPSs or the transformers. They each have their own expertise that they've worked on in their own silo. When you're talking about an entire power architecture and cooling architecture that have to work as one system, communication across these layers is going to be more important in the future. Um, for instance, a valve on the cooling side can take about 30 seconds or a minute to open up,
Mm.
and but power loads on the power supplies can ramp up in seconds. So having advanced knowledge of how these systems can interact together will end up in a more reliable and a more manageable system.
Yeah, yeah, absolutely. And when it comes to liquid cooling as well, how is this changing facility-wide design assumptions?
So liquid cooling is finally here. I mentioned yesterday, cooling is finally cool. So I'm finally a cool person. Um, when you think about air cooling, it was a relative soft way to cool servers. You were able to move the air into the room, and another design team put a crock or a craw in the corner and takes the heat out of the building. When you look at liquid cooling, there's two things that happen. One, you have a much more direct connection to that heat source. So that enables you to actually make a much more efficient system. Liquid cooling leads to much higher levels of efficiency. It can also lead to elimination of water evaporation from data centers,
Mm.
elevated supply temperatures, and all these systems will allow for more sustainable, more energy efficient data centers, which in the end also give more economic benefits to the operator. But at liquid cooling, it's a new architecture. to some, where you now have to use manifolds in the racks. You have to think about liquid cooled servers, we're thinking about liquid cooled power supplies. When the entire architecture shifts to capturing as much of the heat with the liquid cooling loop as possible, this becomes one intimate integrated design. And it's very exciting for me that we made the acquisition of Boyd Thermal, which really brings an expert high volume manufacturing company into the Eaton portfolio, where we can now work as a team together. And I must say, it's already been a lot of fun.
Fantastic. That's great. And we touched around the liquid cooling side of things, but what about power infrastructure for these much higher density workloads that we're seeing?
That's a very good question. Um, Actually, many of the elements that we have in our data center today have legacy roots that go way back into the telecom standards that come from a long time ago. For instance, 48-volt bus bars work really well for lower loads, but are a little bit difficult when you go to 100 kilowatt, or 200 kilowatt, or even 600 kilowatt per rack, let alone higher. So we're exploring liquid cooled bus bars as solutions where you have to run liquid cooling through the copper, as the current in the copper might go from 1200 amperes to maybe 4000, 8000, or even higher. For me as an engineer, it's exciting and also very interesting to see these extreme high amperages coming into server systems. But if you do the simple math, if you want to get um, 200 kilowatts or 600 kilowatts at 48 volts, you're going to need a lot of amps.
Mm.
And amps drive with I squared R losses a lot of heat. So we need to try to keep the temperatures down, and that's why we think of liquid cooling the entire power architecture. And that's a very nice synergy where we currently think about liquid cooling mostly focused on the chips.
Hmm.
We feel that a lot of elements in the power architecture can also greatly benefit from a liquid cooled solution.
Yeah, yeah, absolutely. And we've had quite a few kind of discussions in the studio about how the 1 megawatt rack is on the horizon. So, what power and cooling decisions should organizations be making now to prepare?
Yeah, it's just the 1 megawatt rack. I just want to pause on that because that's so much power.
Yeah.
I once asked ChatGPT, and I'm not sure if it's correct, but what does a Tesla use at full speed on a highway? And it's about 25 kilowatts, right?
Oh, wow.
So
Okay.
you think about 1 megawatt rack, it's 40 Teslas in a box that just generate heat,
Yeah.
right? And 1 megawatt is hard to fathom. It's 1,000 washers or dryers, and you put it all in a box, and that's the heat I got to carry off. I think when we're looking at those levels of densities and already at 200 or 600 kilowatts, it really requires companies that have a tremendous depth of engineering expertise to manage such a problem, because you have to provide power at an extreme level of security and provide cooling at an extreme measure of quality. So the quality of engineering when you go to a 1 megawatt rack will be the threshold to get into that space will be significantly higher. And I'm very excited, when I looked at Eaton with their aerospace background, similar to Boyd, that we do power aircraft, we power trucks, we power automotive systems, and bringing that expertise now to the data center space, which used to be much lower power. Actually, a 600 kilowatt rack, if you take the volume of the rack, which is about 1.2 square meter, and 600 kilowatts, you're almost at the same energy density as a four-cylinder car engine. And we have the expertise to bring power to that and cool it. So I think from an engineering quality level, there's a huge threshold to get into that space, because everything has multiplied by 100x and how much power and cooling you need. Now, it also you have to think about the real estate. If I look at a one-use server and the amount of fluid I need to bring in, um, have you ever been to a data center?
Yes, I have. Yep.
Well, one with liquid cooling, we're now looking at pipes that are 4 inches, and then we go 6 inches.
Yep.
Um, at some point, you're going to run out of space. So we are looking at advanced cooling solutions and advanced power solutions, higher voltage, advanced conductors, and these are all mechanisms to bring megawatt power and bring megawatt cooling. One of the unique things is I was once asked, why are we going to such high energy density? Can we not just do 110 kilowatt racks? And it's the economic output from an AI training algorithm is much, much higher when the chips are closer together, because it's the latency, the communication time between the chips
Mm.
that actually drives half the solution time. So if you're able to pack it very closely, people will keep on densifying the system. And unless we find a way to break that technology, which I don't foresee for another maybe 5 to 10 years, we will keep on densifying our systems because it adds tremendous value to the AI operator. And I think that's what it's all about, delivering value at a reliable, high quality system that can manage such enormous loads.
Yeah, yeah, absolutely. Well, Peter, thank you so much for joining me. I hope you enjoy the rest of the event.
Thank you so much. It's been a pleasure.
Thank you very much.
Yeah.
Thanks.